So in this lecture, we're going to look at the reactions of allyl groups, and we're going to really just focus on the standard reactions of that we've seen in organic 1 using allyl halides. So I'll even just kind of phrase this. So standard reactions of allyl halides. And this includes, when I say standard reactions, I'm going to talk about Sn1, Sn2, and a new one, which is Sn2 Prime. But we'll focus first on Sn2. So let's look at an allyl halide where X is equal to chlorine, bromine, or iodine. This can undergo substitution with a nucleophile, where the nucleophile displaces the X group to give rise to this species here. We could draw curly arrows for this, where the nucleophile attacks the carbon that's directly attached to the halogen atom. So this is direct substitution at the allylic carbon. And this works because the X group is a good leaving group. What's cool about allyl is that allyl halides react more quickly much more quickly than the corresponding alkyl halides. In fact, I don't even know if I've never put my hands on, well, I always wear gloves. No, sorry. I've never opened a bottle of allyl iodide. I wonder how stable it is. But what I'm getting at here is if you had something like allyl bromide, we would say that allyl bromide reacts faster than the corresponding alkyl bromide. And we can even keep steric hindrance about the same or even make it less if we want to. But we would still see a faster reaction with a nucleophile where the nucleophile displaces the bromine atom. Now, an alkyl bromide is still pretty quick to react with a nucleophile. So maybe you won't even notice it that much. But it turns out that this even works for alkyl chlorides. If you take an allyl chlorides, if you take an allyl chloride and treat it with a run-of-the-mill nucleophile, you will get a pretty good reaction. So I'll just write reaction occurs. It's a slower reaction than we would see for allyl bromide. But it's pretty cool because, you know, one thing I don't spend a lot of time talking about in organic 1 because it throws people off is that chlorinated carbons don't generally, normal carbons don't generally undergo substitution reactions that quickly. So I would say that this is very slow when we have a normal alkyl halide, or alkyl chloride. But when we have an allyl chloride, the reaction occurs. It's not the fastest reaction in the world, but it's practical. Like you could set it up and see the substitution occur. So let's make note of that. Allyl chloride will react on a practical time scale whereas alkyl chlorides react too slowly. In fact, we use dichloromethane. I mean, that doesn't really have that much steric hindrance when you think about it. We use dichloromethane as a solvent. Okay, so that is kind of the Sn2 reaction. The gist is it's the same Sn2 reaction that we know and love, but it's faster when we have an allyl system. let's move right into the next reaction, which is the Sn2. I'm gonna put a quote or an apostrophe up there. That's the Sn2 prime reaction. So the Sn2 prime reaction this is a reaction where we see a nucleophile attack an allyl system, not at the carbon bearing the halogen, but at the carbon as part of the alkene. We then push the electrons from the double bond over to make a new double bond and kick off the leaving group to avoid breaking the octet rule. That's going to give us this species plus X minus. Now, what you might say is you might recognize that in this case, this would be the same it appears to be the same as the Sn2 product. And that's because it is for the allyl parent compound. That is, if we add more substituents to make this more complex, we could now see a difference in the products, where if we have a good leaving group, and let's put 2 methyls on the left, maybe you'll recognize this as a prenyl group. So if we add a nucleophile here, the Sn2 reaction will give us this product, whereas the Sn2 prime will attack over here, push the double bond over, push the leaving group off. And then I should have drawn the curly arrow before. That's different than if we just attacked the allyl carbon directly. So this is Sn2 prime. Now the product of this is going to be a bit different. We're going to have a nucleophile here. So this represents another type of reaction. It's a substitution reaction, I suppose. I mean, we're substituting the leaving group carbon with a double bond and then adding our nucleophile to a double bonded system. Okay, so we get a different product. That's the key takeaway here. So different product forms. Now, what I want to emphasize here is we could, when we have these types of opportunities available, I want you to be able to propose both pathways. So if we have a predict the product question with an allyl system, like let's say I've got this and I add it to, let's see, kind of a good run-of-the-mill nucleophile. Let's just go with NaOMe, sodium methoxide. Cross out the sodium, give the O having a negative charge. What I want you to be able to do is draw the Sn2 and the Sn2 prime products. So the Sn2 is where we just replace the bromine with that atom that has a negative charge, and that's different than if we did the Sn2 prime pathway. And I'll draw the Sn2 prime arrows. We're going to add to the double bond, push the double bond over, push the bromine off. That's going to put the OMe down below. And that's different than the negative charge attacking here. So this one on the left would be Sn2 and the one on the right would be Sn2 prime. So we want to be able to predict both pathways. It kind of depends on the situation which one is favored. And I won't go into that now. I just wanted to make us available or recognize that this is possible. Okay, so the next reaction to look at is the Sn1 reaction of allyl systems. So Sn1, whenever we hear that, we want to think about a carbocation intermediate. And so for us, we're going to have allyl with some leaving group, and we're going to let this leaving group simply walk away, taking its electrons with it to leave behind a positive charge at the allyl carbon. We could draw resonance structures where we swing the electrons over to give rise to a different structure. And we could show these in brackets where the positive charge is on the left. So the positive charge could be on the left or the right. Now in this first example, we get the exact same outcome. Now what I want to do is, first of all, I'm going to label this as an allyl cation. What I want to do is kind of remind us that this is impressive that this happens at all. Because the halogenated carbon appears to be primary. And if it's primary, that looks kind of like a 10. Sorry, let me just clean that up a second. Primary. Primary won't form cations. So we won't let that leaving group just walk away and form a carbocation, because the carbocation would be too unsubstituted and too unstable. But even though the carbon appears to be primary, we have to remember that it's not primary. And I'm kind of screaming this at myself. It's not primary, it's allyl. Sorry. It's allyl or allylic. That is to say, we have the opportunity to stabilize that positive charge through resonance as opposed to through substitution. So it's stabilized by resonance and not substitution. Okay, so it's a stable carbocation. So that means we can do this reaction. So what does an Sn1 look like? An Sn1 reaction uses poor nucleophiles. Poor nucleophiles that are weak bases. I think about that. There's a lot of examples, but my go-to example for a poor nucleophile and a weak base would be water or an alcohol. So what that means is we could take an allyl bromide, for example, and react it with methanol and go through an Sn1 pathway to give rise to this product. The mechanism for this looks like this. With bromine, it walks away to give rise to the carbocation. The carbocation is stabilized by resonance. I won't draw those here. The lone pairs on the oxygen atom will engage the positive charge of the allyl cation to form a structure with an oxygen bearing a positive charge. Why positive? Well, it took with it the hydrogen atom that we have to lose in the last step. We do want to show that protonation step as a separate step. I lost a carbon. Goodness me. Okay, I'm going to redraw this. I'm going to remind myself that I've got 3 carbons in allyl. This was where the positive charge is. That's now connected to oxygen. Common mistake by students, including professors and that sort of thing. Okay, we don't want to lose carbon atoms. It's easy to do because of bond line structures. Oh, I don't need the hydrogen in the last step. Focus on what I'm doing. Okay, so the hydrogen is going to fall off to neutralize the oxygen, now having 2 lone pairs in the product. Okay, so that's a mechanism. Now what's cool is if you add substitution to one side, you will get a mixture of products. So Sn1, on this species, we would see the formation of methyl ether. Methyl ether at this position, and then a methyl ether at this position. So let's consider that mechanism. Well, in this mechanism, we really want to take advantage of resonance structures. We didn't have to before. Maybe it would be prudent of me to have done that because then we could get in the habit of it. But the first step is the loss of bromine to give positive charge at this position. But we can actually move that positive charge using resonance to the other side. We'll put our electrons on the, our arrow on the electrons, shift them over one carbon to push the positive charge over on the left side. Because we have substitution, these structures, these resonance structures show that the kind of adding to the left or the right carbon makes a difference. And these resonance structures show that it's possible. So what I'm trying to say is the methanol molecule has a choice to add to the left side or to the right side. Do I say it could add to the molecule on the left or the molecule on the right? No, I don't want to say that because that implies they're different molecules. These two depictions depict the exact same structure, but, these two molecules depict the exact same structure, but they show different properties of that same structure. Now, what we can do is we can add to the left side of this molecule with our blue arrow, or the right side of our molecule, left side with the red arrow, right side with the blue arrow, and get different intermediates. Now, these different intermediates will then get to our separate products. By losing the hydrogen atom. Okay, so this is allyl. In allyl, we have the opportunity to kind of take advantage of adding to one side or the other. And sometimes those sides are different and sometimes they're the same. So those are kind of the reactions of allyls that I wanted to look at just ever so briefly before we move into other types of chemistry. Okay, that'll do it for this lecture.